applications of electric and magnetic fields. All right, so let's start. Okay, can you please read this? Uh, may I ask Sardar to read lesson 8.3?
Me?
Yeah, Sardar.
Okay. Magnetic force on a current carrying conductor. When a current carrying conductor is placed in a magnetic field, it experiences a force due to the interaction of the field with the moving charges in the conductor. This force is given by F equals ILB sine theta, where F is the magnetic force in newtons, I is the current in the conductor in amperes, L is the length of the conductor in the magnetic field in meters, B is the magnetic field strength in teslas, theta is the angle between the conductor and the magnetic field.
All right, thank you, Sardar. So, okay, if you can recall your topic about the current, the resistance in, and the current and the voltage during your grade 11 this. Okay, are you familiar with the current, by the way? This one, or this is the first time that you encounter the current, the I. So
Yes,
no. Yes,
absolutely.
already discussed that or not. You're not familiar.
No, I think the first time, unfortunately.
Oh, this is your first time to see that.
I might have seen the concept of current in my school in Turkey, but I didn't learn it very much, so I am not sure about
Oh,
it.
okay. So in this lesson, you're going to discuss the current in a conductor. Okay. So let let's move on. Okay. Before I show you this problem, I mean before we uh solve this problem, so I'm going to show you a video about magnetic force because in the video it is very much explained, and so that because there are different I mean different figures where you can um, uh, easily learn the magnetic force. So let me stop this and show you the video about magnetic force. Okay. Or force on a current carrying conductor. So this is just a 3-minute video. Okay, this one.
In this video, we'll talk about the force on a current-carrying conductor in a magnetic field is produced due to the flow of an electric current through a conductor. A force is exerted by this magnetic field on a magnet which is placed in the surroundings of the conductor. According to a French scientist, André-Marie Ampère, an equal and opposite force is exerted by the magnet on the current-carrying conductor. Let's go through an activity to demonstrate the force which is caused due to the magnetic field acting on the current-carrying conductor. We need a small aluminum rod, AB, having length about 5 centimeters. Suspend it horizontally on a stand using 2 connecting wires as shown. Take a horseshoe magnet and place it in such a way that the rod lies in between the 2 poles of the magnet with the magnetic field directed upwards. The north pole has to be vertically below and the south pole has to be vertically above the aluminum rod. In series, connect the aluminum rod with a battery, key, and rheostat. Now, let the current pass through the aluminum rod from B to A. We will notice that the rod moves towards the left direction. On reversing the flow of current, we will observe that the rod moves towards the right. Through this activity, the conclusion can be made that when a current-carrying aluminum rod is placed in a magnetic field, force is exerted on it. It can also be concluded that the direction of force is reversed when the flow of current is reversed. If the poles are interchanged, the direction of force acting on the current-carrying conductor gets reversed. This shows that the direction of the force on the conductor depends upon the direction of the current and the magnetic field. When the direction of the current is at a right angle to the direction of the field, the magnitude of force is at the highest. In such a condition, we can use a simple rule to find the direction of force on the conductor. In this activity, the direction of the current and the magnetic field are considered to be perpendicular to each other, and from this, it can be found that the force is also perpendicular to both of them. The Fleming's left-hand rule helps us to illustrate the direction of force acting on the conductor, magnetic field, and the current in a simple manner. According to this rule, stretch the thumb, index finger, and middle finger of your left hand such that they are perpendicular to each other. If the index finger shows the direction of the magnetic field, then the middle finger shows the direction of the current, and the thumb shows the direction of the force acting on the conductor. Electric motors, electric generators, loudspeakers, microphones, and measuring instruments are